Hello everyone, welcome to our new AI weekly podcast video from NeuronTree.AI. So in this video, actually we are going to present a paper related to explainable AI. In our country like Bangladesh, basically most of the researcher use explainable AI just as a template. Most of the 90% of the people use some traditional methods like Grad-CAM, Grad-CAM++ or Lime, SHAP as a template. For example, I'm importing the model and I'm giving an input image and model is giving me an output. This is how everyone does in our country. But the problem is actually it's not the effective way to learn XAI. So that's a big problem in our research community in Bangladesh. But in other countries like Korea, many people use XAI and they are creating billion-dollar startup based on this. So to work on XAI, we have to understand how it works and how we can effectively apply in AI domain. So as I'm from XAI lab, and I think my professor is one of the best in this field in the world. So I will try to help to guide some students in our country. So let me share. So today I'm going to present this paper, layer-wise relevance propagation and overview. So this LRP method is one of the most popular method in XAI, and many professors really like this method, and they try to use it in industry, in not only in research but also in real life scenario. So I'm Sakib Hossain, co-founder and CEO of NeuronTree. So let's start for today's session. So this is the contents of today's lecture: background motivation, introduction to LRP, LRP rules, LRP evaluation, and conclusion in the end. So let me talk about some background motivation first. So in machine learning, a common problem is spurious correlation in high dimensional data. So what is spurious correlation? For example, there are three figures here, 1, 2, and 3. Here, the first one is only the correct, but this 2 and 3 is wrong. Here, model predicted or classified data correctly. For 2 and 3 cases, model also classified the data correctly, but in the wrong way. So here, this decision was made mostly influenced by X1 feature, based on this point on the X1 axis, this vertical line divided the data easily, and this is true data distribution. And for this vertical line, model classified the data genuinely. But here, model also classified the circle and square shapes, but the problem is how it made the decision. It was wrong. It was highly influenced by X2 feature. So based on this point, horizontal point, it classified those data, but in the wrong way, because the true data distribution should belong in this way, so which was correct in this plot. So similarly here, both X1 and X2 influenced this decision, though it correctly classified those data, but it's wrong. So this is spurious correlation, and because of the large data set, it's very common scenario. So what's the solution? So one solution is like a feature selection. Here what we can do, we can only present the model with good input features, but the problem is in practice it's not easy. For example, in image recognition, suppose individual pixels do not have any fixed roles. What does it mean? For example, if we want to classify a binary classification problem, suppose we want to classify whether it's dog or cat. So in dataset like cat images, for cat there are many thousands images of cat, and when we capture this cat image, we capture this image from different angle. So always the pixel value is being changed. There is no fixed value. So in one image, cat's nose in one position, but in other image the nose is in different area. So this is the problem. So this is the problem of feature selection. So here it comes the term explainable machine learning. Here we want to train the model and examine later. Here it's not important. We don't care about the feature selection during training. We want to train the model first, then we will examine the model we can remove the bad features later, and model can be retrained on the clean data further. So this is the motivation of explainable machine learning model. So particularly, let's talk about LRP. Here we can see a diagram. So first of all, like, what is LRP? LRP is an explanation technique which propagates the prediction using some rules. So this is the equation, like Rj equal to summation of k zjk divided by summation of j zjk into rk. Actually, we will discuss this equation in the further slide. And here only we can remember zj, it quantifies the amount of contribution node j has to make node k relevant, and rj is the final aggregated explanation score for neuron j. So we can remember another thing. For example, if this neuron has 10 units, it should be redistributed to these layers equally. Suppose like 5 and 5, something like that. So move to the next slide. In LRP, we have to remember one thing, which is conservation property, which is very important to maintain in LRP. That means that I already discussed. If this neuron receive like 10 unit, it must be distributed to the lower layer in equal amount. However, we can derive this LRP from deep Taylor decomposition. So let me talk about some mathematical intuition. First, we need to decompose a neuron signal using first order Taylor expansion. So let's say this is the equation of pre-activation signal of to neuron k, like zk of a equal to summation of j aj wjk plus bk. You may have heard like w equal to mx plus c. So this equation is the same. So for pre-activation signal, we can write the equation like this. Now this term comes the first order Taylor expansion. So we have to use this first order Taylor expansion in our equation. So we want to expand zk around a chosen reference point where zjk of a tilde is equal to 0. So what does it mean? So we can write down this equation like this: zjk equals to zjk of a tilde plus summation of j aj minus a tilde j into a derivative of zjk with respect to aj. So if you find difficult to understand this equation, you can easily think about in reverse way. For example, this term is 0, and we can, as we mentioned, we are writing this term aj is like this: aj minus a tilde j. And if we derive this term like aj with respect to aj for this whole part, we only get like wjk, because with respect to aj this is going to be 1, this is going to be 0, we get only wjk, and here this term is 0. So finally we get aj wjk. So we can easily find this equation from here. Now, as I mentioned, we can get the derivative result like this, and yeah, we can get something like this as we already saw here. Now we can write this term as like this: summation of j rjk. Here rjk that j sends to k. So yeah, so let's move to the next slide. Now we have to propagate the relevance rk. So here, like for like rk, whatever it receives, it must be redistributed. So here if we want to calculate the relevance for j equal to some, we can write something like this. What does it mean? So exactly what we have seen so far: wjk zjk divided by summation of j zjk into rk, and that means like contribution of rjk divided by total signal zk into received relevance rk. So if you compare that equation and follow this diagram, I think you will easily understand how it works. So from this equation, we can easily get this equation as we already saw in the initial slide for the LRP equation. and this equation simply represents LRP zero cases. Here we are we assume a tilde j is equal to 0 or bias bk is equal to 0. So we are cancelling this part, so we get the equation like this, and it represents LRP zero rule. We are going to discuss these rules in the further slide. So from this equation, if we cancel out the common term, finally we get something like this. That means summation of j rj equal to summation of k rk. So it satisfies conservation property. So here, I mean, like as I discussed, so in every layer the amount of unit it receives, it should be same for the following layer as well, because it maintains conservation property and it redistributes equal amount of unit to the lower layer. So this is the proof how it maintains conservation property. Now let me talk about some LRP rules. So as we already saw, and we for LRP zero rules we get something like this, and if we extend this equation, we can write down like this: zjk means ajwjk, as we saw in this slide. So and here this 0, it includes the bias term, and as we know, for LRP zero rules we are assuming bias bk is equal to 0 and a tilde is equal to 0. So we get something like this. And for LRP epsilon, actually it aims to solve gradient noise by introducing a small positive term epsilon to its denominator. Actually it absorbs some relevance when contributions to neuron K are weak or contradictory. So it helps to reduce the noise. So we will see example in the following slides. And this is another rules, which is LRP gamma. So here it introduces this term to wjk. So actually it favors the effect of positive contribution over negative ones. So this rule was mainly proposed to boost positive weights so that it can give more stable explanations. So here it just add this parameter to wjk to just boost the positive contribution over the negative ones. And now let me talk about LRP evaluation. So actually the authors, they focus on mainly on two explanation properties. One is fidelity and another thing is understandability. What is fidelity? Suppose BGG16 classifies an image as a cat. So this is fidelity. If it classifies well cat image, we can say the fidelity is very good. And understandability is related to interpretability of the explanation to human. So as a human, can we understand from this heat map, is it a cat or dog? So yeah, this is understandability. So for LRP zero rule cases, if we see an example here, the main objective is the castle. Remember, the main objective is the castle. But this rule, it fails on the castle part. We don't know what is here because there are many dense representation. So it clearly lacks fidelity because model couldn't correctly classify the castle here. Also, explanation is not sensible. We cannot understand where there is a castle or not. So it lacks understandability. However, this positive relevance is represented by the red color, and the negative relevance is represented by the blue one. For LRP epsilon rule, we can see it really reduced a lot of noise here, as we discussed in the equation. But fidelity is still low because you have to remember, model, the main objective is castle here. But beside castle, there are many other things like this area model tried to classify as a positive one. So we can say the fidelity, it has fidelity but low. And also for the explanation, we can say, yeah, but we can moderately understand there is a castle, but we cannot be 100% sure is it a castle or not. But yeah, it's a moderate one in terms of understandability. And for the LRP gamma rule, we can see here this lamppost is highlighted too much alongside the castle. that means actually it lacks fidelity. Yes, we can easily understand there is a castle, but because of this lamppost, the the decision of the model is wrong, so it lacks fidelity. And explanation is, I will say it's reasonable, because as a human we can understand this is a castle. So, and another rule is composite LRP. So first, let me talk about what composite LRP is. So composite LRP is like author try to apply different rules in different types of layer, like early layer, middle layer, lower layer, and uh, they investigated if they compositely applies these rules according to the characteristics of different layers, model get best visualization. So here in this image we can easily see the castle, also this lamppost is not being seen here. So overall, compared to other rules, this rule really performed great. So we can say it has good fidelity, also understandability. So in conclusion, we can say like it strictly follows the relevance conservation law as we discussed earlier, but the problem is heuristic challenge. I mean, optimal results can currently require manual heuristic selection of rules, introducing bias and complexity. As we saw here, we have to select manually for different layers. So this is one of the problem. So based on this conclusion, there are many scopes to develop new rules or to work more on LRP paper. However, I think this session will help a lot of you who particularly want to learn explainable AI, and I will continue and post more contents on this explainable AI. And many of you maybe already know, in our NeuronTree there are already many teams and they are working on explainable AI. So we are trying to uh, develop different core contribution in research on explainable AI. So yeah, even for the LRP, there is a team in our NeuronTree. So check the video carefully. I know many of you can find it a little bit more complex, especially in our country Bangladesh. But the thing is, like in top university like in KAIST or in different country in USA or Singapore, Korea, Japan, actually their culture is different. They always try to present different state of the art papers. They focus on more theoretical part rather than practical implementation. So if we can inherit this culture and continue this day by day, I think one day many of us in our country Bangladesh, we will be able to publish more top conference papers. So yeah, we have to adapt ourselves to understand mathematical property, statistical property, inner property, and then we have to focus on implementing those problems. So I think it will be helpful for many students. So we shouldn't rely on ChatGPT. We shouldn't ask ChatGPT, please give me some answer or improve this model by doing some fine tuning. So we have to get rid of this kind of approach. We have to understand the core property, and based on that, we have to find some solution. So if any of you can find some limitations or future scope to develop LRP rules, feel free to comment or contact us. You can be a member of NeuronTree as a researcher. Thank you. I think that's enough for today. So see you soon.